Hi, thank you for the introduction and thank you for the opportunity to speak at the Sea Lice conference. I'm going to present a study of coupling hydrodynamic simulations to salmon lice population dynamics in Norway and use a case study of production zone 2. This work was done in collaboration between Fiskaaling and Havforskningsinstituttet in Bergen. So the main aim or overall goal in the study is to simulate salmon lice population dynamics on a per farm basis. And we want to do this based on the connectivity between farms. So one of the motivations for this modeling approach is that we have some very good examples from the Faroe Islands. So here you see an example from Faroe Islands. It's a production cycle. And the model is the black line, and the salmon lice are these red dots here. And you see that we managed to model dynamics fairly well in this example, using a number of fish when they reported doing treatments, which are these vertical lines here, and of course temperature. Why this is the case in Faroe Islands, we are not really sure yet, but we expect it has something to do with the dominating tidal forcing. So we have relatively constant parameters over time. Also, we are isolated in a relatively small area, so we know our space, so to speak. And probably also we, or at least at Fiskaaling, we believe that we have very reliable lice counts. But we don't have any sufficient hydrodynamic simulations for the Faroe Islands yet, so we can't try this model on a full scale in the Faroes at the moment. So we did a case study of production zone 2 in Norway, where we have a hydrodynamic simulation from September 1st, 16 to 5th of December 19. And we have production data, lice counts, treatments, and temperature, so everything we need to run this model fully. So we just jump right to a diagram of the model, which is of course based on a lot of previous work. I can mention Stian, Revie, and Adam's approach to simulating lice dynamics. But we have had a lot of problems incorporating, for example, varying temperature in the model. So we came up with a new approach and went from a more stage structure to a cohort or agent-based model structure. So if we take farm 1 here, or a farm, it will get lice from somewhere. And so each time step we make a new lice agent, 1 male and 1 female, and we track the biological age and also count how many lice each agent represents. So after a given amount of time, depending on temperature, they will develop into gravid females and adult males. And depending on number of gravid females and also the temperature, they will make X amount of larvae, which we track in this planktonic agent, for a lack of a better word. And we track it, it's set to track it 40 days back in time now, so we know for each farm how many larvae they produced 40 days back. And then we come to the part where we couple the hydrodynamic simulations to the population dynamics, and we do this by using hydrodynamic simulations that force particle tracking models that can make these connectivity matrices. And you see that there are several connectivity matrices in depth here, which are, depending on how far back you track the larva production, you will have X amount of these matrices in depth. And if you multiply this array with the matrix, you can estimate how much, for example, farm 1, how much farm 1 gets from itself. So this is self-connect or internal infection. So how much it gets from itself, but also how much it gets from farm 2 and farm 3, and so forth. And you can do the same for all 3 farms. And then the cycle completes And we also added a receiving ratio, which I will come back to in just a little bit. And I don't expect you all to understand all the mechanics in the model just by looking at this diagram for 2 minutes, but this is roughly how our model works at the moment. For the particle tracking, we used Norcust 160. Vladim 2 was the particle tracking model. We released 5 particles every hour from each farm site. The receiving area was 3.3 grids, or 480 by 480 meters. And a particular particle was only counted once in any given connection. And we only, of course, counted infectious coccopodites. And we used the notorious 17% per day mortality. And in order to make these age matrices, we recorded the age of the particle. So for the population dynamic model, as I mentioned, development time is dependent on temperature and mostly based on Hamri et al. Larval production is also dependent on temperature and again on Hamri et al. 19, but also something 16. So the model works as a lot of previous model work. So we have the calamus stage, so you have time, lice per salmon. You have the calamus stage, go to the pre-adult, to adult female, and we have one separate there for egg-bearing adult females. If you do a treatment, a 90% treatment, you will, the numbers will go 90% down on all stages in one instant. But because we don't kill the larvae in the environment and they have managed to build up some internal infection, calamus stages go right up after such a treatment, and they will eventually become egg-bearing adult females. But we also have in that you can give them in-feed, for example, slice, then you will have a higher mortality for some given period, and that dynamic looks different compared to this when you, so 2 different treatment types. We also included cleaner fish. We haven't worked that much with it yet, but we can see in the model how important the timing is of when you put the cleaner fish into the cages in order to control the lice numbers. You can do another experiment to see how temperature is included. So here you see this dotted blue line is the temperature. And if you do an experiment, so take 4 farms, start them at 4 different times of the year, and look 1 year ahead after stocking. You see that if you start 1st of January, you will have the highest amount of adult females after 1 year. If you start 1st of July, you will have the lowest number of adult female after 1 year. If you do another experiment, take all the internal infection away, and just put a high constant external infection pressure. In theory, you should reach equilibrium point, but because this equilibrium point is affected or determined also by temperature, you see that no matter where you start, you will end up at this equilibrium, and they all end up at the same place, and this equilibrium will shift depending on temperature. So for the receiving ratio, we need to solve the problem of, so we have X amount of particles coming into a receiving area, but we don't know how many actually will enter a farm. So we tried 3 different approaches. One was constant, so just say, for example, 15% of all particles that go into the receiving area also attach to the farm. Then we tried type 2 functional response. So initially you will have when you have a low biomass or number of fish, you will have a low receiving ratio. But after some time, it will go up and approach some constant. And we also looked at this receiving ratio as a function of biomass. So we estimated how much volume a farm takes up depending on how much biomass is in the farm. And this initially is also low. But after, so if you have, for example, about 5 million kilos of farm or a fish in the farm, you will take up or receive over 25% of the particles that enter this receiving area. So for the results, we validated our approach. I don't know if you can say in a simple way, but we took the lice counts and looked at, okay, what does the model say that this lice count should be at that particular moment? And we took the period from they stocked until they either put clean the fish into the cages or did their first treatment. And we don't have that many data points left then. And we did it, looked at adult female, pre-adult and adult male, and also when we add this both together to take out the uncertainty of when they shift stages. And we looked at a constant receiving ratio, a type 2 functional response, and also the biomass. And we see here that we get a quite high R square in this when we add them both together and use biomass as a function of receiving ratio. If we do the same, but now just until they do the first treatment, we get a lot more data points, but now the R square is down to 0.8. And if we look at, maybe it's not that clear here, but if we look at the R square for each farm, most of the farms that are very badly correlated with the model are found in the fjord canals. If we look at the difference between the model and the data over the simulation period and take the mean difference across all farms, we see that we overestimate the lice counts, or the model overestimates the lice counts quite a bit, at least especially in this warmer period here in 17. The difference is lower when the temperature is lower, and the model has a tendency to underestimate the lice counts in also those periods. But here we see that the largest difference are found in farms that are located inside the bay of the fjord system. So just to show some concrete examples from the simulation. So first here, two bad examples. So here we have temperature again, number of fish, and these vertical lines here are when they did treatments. Blue line is the model, and the red are the lice counts. And we see that we don't hit the dynamics here at all well. We overestimated a lot in the start, same here. But if we take two good examples, maybe especially this one is quite good, at least initially. So we hit the same dynamics, they go up at the same time, and also we do a treatment, and then it goes down, and the model goes up, and also the lice counts go up. But somehow the adult female mysteriously go down to 0 again, even though they haven't reported any treatments or stocking of cleaner fish. So we of course have that problem as well when we do these models. So maybe we're not there yet that we can sufficiently simulate on a per farm basis the dynamics, but then we try to look at the whole of production zone 2 and looked at the total amount of adult females and also the cumulative treatments in this simulation period, so from 16 to 19. And if we then take our model and start it, in this case we started it by giving all the farms that were present in the water for the first 200 days of the simulation period, we gave them 30,000 lice per day to get the model up and running. And we said, okay, everybody has to treat when they hit that threshold of 0.5. And we looked at the efficiency of 90, 70, and 50%. And we get fairly good dynamics, especially in this last period here, compared to the data, the red line. and the cumulative number of treatments needed are fairly similar when you have an efficiency of around 70%. So we can expand on this maybe a bit, the threshold. So I often hear that people say you can't go down in the treatment threshold because you'll need to just treat endlessly. So I tried to look at this question in this model realm, and I took the same, so a treatment efficiency of 70%, and then treatment threshold of again 0.5, and then one treatment threshold at 1.5. So of course you have a lot more adult females if you use the threshold of 1.5, but the number of treatments needed to keep this threshold is almost identical or very similar in both cases. We can expand on this further. So in some sense, you can say, if you look at this graph, you say, okay, if we go too low in treatment threshold, so down here is 0.005 treatment threshold, even though the lice counting system wouldn't allow that low of a treatment threshold at the moment. But if we went down here in the model, yes, it looks like we have a lot more treatments. But if you look at the simulation period and you look at treatments needed per 30 days, you see that most of the excess treatments that are here are actually in the first period of when you gave all the farms 30,000 lice per day. But after a while, almost or all treatment threshold enter the same dynamics and need almost identical number of treatments to keep their thresholds, so to speak. And here we haven't even looked at the LA effect or the effect of the chances of a male finding a female if we have a low treatment threshold, which would of course talk in the favor of going lower in the treatment threshold. And we also assumed here that we don't have any external, so after the first 200 days we gave a lot of lice, but after that we had no input from the environment or wild stocks of lice, which of course would set some kind of lower boundary of how low you can go in treatment threshold. So in conclusion, simulating dynamics on per farm basis in real time is maybe not that sufficient yet, but we believe we are within a realistic range. If we look at some sources of error, it's really hard to pinpoint. It could be that a hydrodynamic model doesn't capture connectivity correctly. It could be that the lice counts may not be representable. And it could be that a population dynamic model is insufficient, or it could be a combination of all three. But I think we can simulate the whole of production, simulating the whole of production zone 2 looks reasonable. And regarding treatment threshold, it has a very small impact of the number of treatments needed if you look long term. And we haven't even included the LA effect here so far. So thank you for your time. And if you have any questions, just contact me. And the model is available on GitHub, and we would love to have a collaboration with people, or if people want to contribute to the model. So just contact me afterwards if you have any questions.